Right, in this video, we're going to look at two very important graphs with the photoelectric effect and the significance of, in particular, the gradient of those two graphs. Okay, so let's have a little recap. Again, this is a Google Doc I'm going to share with you. I'm just going to go through and annotate it as I would expect you to do as well for your own notes, really. So anyway, photoelectric equation, okay, one of the most famous equations of all time. I mean, arguably, it's Einstein's second most famous equation after E equals mc squared. But this is the equation that got Einstein the Nobel Prize for Physics in, I think it was 1921 or 22. Anyway, right, the photon energy, it's all due to conservation of energy. So the total energy you start with is your photon energy. That gets split up. Some of that overcomes the work function. The remainder is given as kinetic energy of the fastest electrons. Okay, so there you have it, the photoelectric equation. Right, now if we have electrons emitted with the lowest possible frequency, so if we take this frequency down to the lowest possible value, then electrons are going to be emitted with zero kinetic energy, aren't they? So as we saw when we played with the animation yesterday, as we saw, when the frequency is the threshold frequency, that's F0, then the photon energy is exactly equal to the work function. So it's a very, very useful way, a very easy way of measuring the work function of your metal, okay, using your photocell. Right, so now graphs. Like I said, there's two very important graphs we need to look at today. If we take the photoelectric equation and if we rearrange it to the form y equals mx plus c, okay, it's kind of close, but I want to make this the x variable and this the y variable. Remember, that's a constant for your metal. Right? If you have a metal and you're varying frequency and seeing a range of EK maxes, that's always constant. So I want to make this the subject of the equation. That's our y. Okay, let's do that. So, where is he? There it is. So let's start with, what was it? HF equals phi plus EK max. Okay, what do I want? I want to make the EK max the subject. So EK max is equal to, now it's HF minus phi. Okay, now if we plot, okay, if we plot EK max on our y-axis and frequency on our x-axis, we get a graph like this. Okay, because these are our y values and these are our x values, what are we going to get? Well, we're going to get a straight line with a gradient of h. So the Planck constant is going to be the gradient, and we're going to have a y-intercept, a negative y-intercept of the work function. So the graph looks like this. Okay? So it's a linear relationship. It's a straight line. Now, we usually, okay, let me just write where we've got E, K, max. That's our y-axis. We've got the frequency of the light in hertz. That's our x-axis. What's that point there? What's the point? What's the value of frequency? It cuts the x-axis. You'd be right in thinking it is F0. That's our threshold frequency. Now, when you draw this graph, you usually have a dotted line because you can't have negative kinetic energies, can you? All right. So that's a dotted line, but mathematically, where it cuts the y-axis, the kinetic energy axis, that's our value of work function phi. Okay, but the really, really useful bit, the important bit, is the gradient. Now the gradient, in this case, okay, is h. And that's how you find your Planck constant. So there you have it. Okay, so a graph of maximum kinetic energy, EK max, against frequency. I'll give you a graph like that. Now, like I said in previous videos and previous lessons, we can't measure EK max directly, can we? Okay, because EK max is found out from the stopping potential. So if you remember, if we have our photocell, now remember, if we want to use the photocell to measure the stopping potential, then we have to reverse the polarity of the battery, don't we? So that should look like that. Okay, and then we turn the voltage up so that the current will drop to zero, and when it just drops to zero, we've then got our battery measuring stopping potential Vs. Okay, because remember, this is the negative terminal. That's negative, so that's going to be pushing the electrons back. Right, so values-wise, if you remember, okay, if we are at the stopping potential, then we have EK max. That's the work done on the fastest electrons, because that's that's all the kinetic energy that's taken away. That's equal to the charge on an electron multiplied by stopping potential. Okay, because work done equals charge times voltage. So we can go back to this equation here and substitute for EK max, can't we? So this gives us, instead of EK max, we write E Bs. And that equals, what does that equal again? It's HF minus phi. So HF minus phi. Just one last thing, we're going to get the E over to the right hand side. So Vs equals H on E times F minus phi. Okay, that's slightly better, because now we can plot a graph of two things we measure directly. So we're going to measure stopping potential and plot those on the y-axis. We're going to measure the frequency of light and plot those on the x-axis, which means that the gradient of our straight line is h over E. H being Planck constant, E being the charge on a single electron. So there you have it. All we need to do now is plot the graph. And it looks very similar. But this time we're plotting stopping potential against frequency. And again, it's a straight line. Again, it cuts the x-axis at f0. This is not the work function. Okay. I've just made one mistake. Has anyone spotted my deliberate mistake? You have? The y-intercept is phi over E, isn't it? Ooh, cheeky. Anyway, right, so yes, the y-intercept is indeed phi over E. Okay, but the gradient, what's the gradient again? H over E. Okay, gradient equals H over E. So if we're going to plot stopping potential, which is something we can measure, against frequency, which is something we can measure, we get our straight line, and that's how you find that's how you find Planck's constant in practice. Thank you very much.